Grid congestion is one of the least discussed and most destructive forces in green hydrogen development, not because it is dramatic, but because it is invisible. Hydrogen projects do not usually fail when a transformer explodes or a transmission line collapses. They fail quietly, slowly, and bureaucratically as power that looks cheap on paper becomes inaccessible, unreliable, or unusable in practice. By the time developers realize grid congestion is the real problem, capital has already been spent, timelines have slipped, and final investment decision is no longer within reach. Most green hydrogen narratives assume that if renewable energy exists nearby, it can be used. Solar farms are built, wind turbines spin, prices appear low in regional averages, but grids are physical systems, not spreadsheets. Electricity must move through transmission lines, substations, interconnects, and markets that were never designed to accommodate large, continuous industrial loads like electrolyzers. When hydrogen projects collide with these constraints, congestion becomes the silent killer. Grid congestion occurs when electricity cannot flow freely from where it is generated to where it is needed. This happens when transmission capacity is insufficient, interconnection queues are long, or multiple assets compete for the same limited infrastructure. In renewable-heavy regions, congestion is often a sign of success. Too much generation has been built too quickly for the grid to absorb it. For hydrogen developers, however, congestion turns apparent abundance into operational scarcity. On paper, congestion can look beneficial. During periods of excess renewable generation, wholesale power prices may drop to zero or even go negative. This is often cited as an opportunity for hydrogen to soak up surplus electricity. But in reality, congestion often prevents that power from reaching hydrogen facilities at scale or with consistency. Curtailment increases. Dispatch becomes unpredictable. Access to low-priced hours becomes competitive. The very conditions that create cheap power also make it unreliable. Electrolyzers do not function well in this environment. They are not peaking assets. They are capital-intensive systems that rely on steady operation to remain economic. When congestion forces frequent ramping, shutdowns, or partial operation, utilization falls and costs rise. Developers then face an impossible choice. Either they oversize electrolyzers to capture brief windows of cheap power, driving capital cost per kilogram higher, or they accept low utilization and watch economics collapse from the other direction. Interconnection queues amplify this problem long before a project is built. In many regions, hydrogen projects wait years for grid connection approval. Transmission studies reveal that upgrades are required, often at the developer's expense. These upgrades are expensive, slow, and uncertain. Timelines stretch, costs escalate, off-takers lose confidence. Projects that looked viable at the concept stage become stranded in regulatory limbo. Even when interconnection is granted, congestion risk does not disappear. It simply moves downstream. Locational marginal pricing means hydrogen facilities may face higher effective power costs than headline regional averages suggest. Congestion charges, uplift fees, and curtailment compensation mechanisms distort price signals. A hydrogen plant may be physically close to renewables, yet financially distant from cheap electricity. This is why co-location is often misunderstood as a silver bullet. Developers assume that placing electrolyzers next to wind or solar farms eliminates grid risk. In reality, co-location solves only one part of the problem. It reduces transmission distance, but it does not eliminate congestion within shared substations, export limits, or grid balancing constraints. If the renewable asset itself is curtailed due to upstream congestion, the hydrogen plant inherits that curtailment. Off-grid solutions appear attractive in response. Dedicated renewable generation paired with electrolyzers promises isolation from grid congestion. But isolation comes at a cost. Off-grid systems must be oversized to achieve acceptable utilization. They must manage intermittency internally. Storage, whether electrical or molecular, adds capital and complexity. The system becomes less flexible, not more. What is gained in independence is often lost in efficiency. Grid congestion also interacts dangerously with policy incentives. Subsidies tied to hydrogen production volumes can push developers to operate during congested periods, even when power costs spike. This creates distorted operating behavior that looks acceptable while incentives last, but collapses when they end. Projects optimized around policy windows rather than grid realities rarely survive long enough to mature. The geographic pattern of hydrogen project success reflects this constraint. Regions with abundant renewables but weak grids struggle to move beyond pilot scale. Regions with moderate renewables but strong transmission and industrial load management perform better than expected. Grid strength, not renewable abundance, often determines outcomes. Yet this variable is rarely foregrounded in hydrogen strategy discussions. Another layer of complexity comes from competing demand. As grids decarbonize, they become more valuable. Data centers, electric vehicle charging, heat electrification, and industrial loads all seek access to clean electricity. These sectors often have higher willingness to pay than hydrogen. In congested grids, hydrogen is frequently the marginal loser. When access is rationed, hydrogen is curtailed first. This competition intensifies over time. Hydrogen projects are typically planned with multi-decade horizons. Grids, however, evolve. A grid that appears uncongested today may become constrained within a few years as new demand connects. Transmission expansion lags behind generation and load growth. Hydrogen projects that rely on static grid assumptions are exposed to future congestion they cannot control. The result is a growing gap between announced hydrogen capacity and operational hydrogen capacity. Projects are announced based on renewable availability and policy support, but few advance to sustained operation because grid realities intervene. Congestion does not generate headlines. It generates delays, renegotiations, and quiet cancellations. Electrolyzers are often blamed when utilization disappoints. In truth, electrolyzers are responding rationally to grid constraints. They operate when power is available and affordable. They shut down when it is not. The technology is not failing, the system is. This is why grid congestion is more dangerous than high power prices alone. Prices fluctuate. Congestion persists. A project can hedge price risk. It cannot hedge physical bottlenecks easily. Transmission upgrades take years. Regulatory approval is uncertain. Cost allocation is political. Hydrogen developers rarely control these variables. Bankable hydrogen projects internalize this reality early. They do not treat grid access as an afterthought. They design around transmission limits, congestion patterns, and interconnection risk. They accept lower utilization rather than chase unreliable cheap power. They build modularly. They prioritize grid-secure locations over theoretically cheaper but congested ones. This approach produces fewer headlines but more durable assets. It also explains why many high-profile hydrogen hubs struggle to move from announcement to operation. Hubs concentrate demand in regions where grid infrastructure is already strained. Without parallel investment in transmission, hubs amplify congestion rather than solve it. Grid congestion also undermines hydrogen's role as a flexibility asset. Hydrogen is often framed as a way to balance grids by absorbing excess renewable generation. In reality, grids that need balancing most are often the least capable of delivering power to hydrogen facilities at scale. The paradox is that the conditions that create excess power also create bottlenecks that prevent its use. Over time, this reality forces a reckoning. Hydrogen cannot be planned independently of grid architecture. It must be integrated into long-term transmission planning, not layered on top of existing systems. Until this happens, congestion will continue to quietly undermine feasibility. If developers want hydrogen projects that survive beyond announcements, grid analysis must be treated as a first-order constraint, not a technical footnote. Transmission capacity, congestion patterns, interconnection risk, and competing demand must shape siting and scale decisions. Projects that ignore these variables are not unlucky. They are misdesigned. This is where system-level thinking becomes essential. Hydrogen is not a standalone technology. It is an electrical load embedded in a constrained network. Success depends less on electrolyzer specifications than on how electrons move through wires under stress. For developers, consultants, and investors who want to evaluate hydrogen projects through this lens, H2 Hub by Renewable Energy exists as an authority platform for system-level analysis. It focuses on how hydrogen interacts with grids, markets, and infrastructure constraints over time, rather than treating hydrogen as an isolated innovation story. For those who want to independently stress test grid exposure, congestion risk, utilization scenarios, and delivery economics, we've linked recommended project finance and planning models in the description. These are optional execution tools for scenario analysis, not inputs to this specific discussion. Grid congestion does not announce itself as a failure. It suffocates projects slowly, invisibly, and decisively. Until green hydrogen strategies confront this reality directly, congestion will remain one of the most powerful forces preventing hydrogen from scaling beyond isolated successes.